let's go. Okay, hello again. I have shared in the Mattermost channel the status, the code as it was before the break. If we can do a recap of what we have done at the moment. So at the moment, we have implemented, sorry, I have to share actually. It will be better if I share. Okay. Okay, before the break, we have created the step in action, header and implementation file, and we have also implemented the event action. Now we left the code in a status that it compiles, but the event action still is not registered in the container of user actions, the your action initialization.cc. So we have to do that. But also we have to connect the step in action to the event action. So the information of the energy deposited along the step at each step will be summed up into the event action. So we will start by adding the event action into the container of user actions. So we have to edit the file source, your action initialization.cc. Okay. And here we have to register the new user action that we just implemented. Our action is not stepping, but event. So we type hash include space between quotes your event action.hh. We copy the keyword. And now we can say your event action asterisk event action equal new your event action. Actually, we have to do it before. Semicolon, set user action event action. Okay. So again, in the file, your action initialization.cc, we have added the include of your event action.hh, and we have added a new object in build of type your event action. At the moment, we don't need arguments, and we register this. Good. Now we can recompile. I will try to keep it open. So this is the lines that we have modified. Okay. We can recompile from the intermediate application directory by saying cmake space hyphen minus minus build. Now you see that we only modified your action initialization. So this is the only file that has been recompiled. Please, if you have not done it before, remember to remove in the macro file Geant4 run.mac the verbosity. You can simply delete this line or put it to 0, doesn't matter, the default is 0. So the Geant4 run.mac will only initialize the run manager and simulate one event. Okay. Now we can execute by doing ./build or application Geant4 run.mac. And what do we see? Now it's a bit more clean output.
How did you turn off the?
Yes. So the question was how to turn off the tracking verbose. So in the macro file Geant4 run.mac, before here we had tracking verbose 2, we can put 0, or you can delete the command itself. It will make the same effect because by default there is no verbosity. And if we go and inspect the output in the terminal, we see a lot of printouts by the step in action, user step in action, energy deposited, blah, blah, blah. And then at the end, we see energy deposited during the event 0. Okay, so this means that the event action was registered in the container of user actions. That is the reason the end of event action printout is being printed out. But we still miss the connection between the event action and the step in action. The step in action has to update the event action with the energy deposited per step. To do so, we have to change 2 files. We have to change the way we construct the event, the step in action, and we have to also change the way we build these 2 user actions in the action initialization. So we will start by modifying the classes, the class step in action. So we open with gedit include your step in action.hh. We go back here. Now we will connect the step in action to the event action. So we will create an internal member of type your event action asterisk, because it will be a pointer f event action. Because we are only using a pointer, we can use a forward declaration. So we type class your event action here on the top, and we will initialize this at the moment of construction. So we will do the same trick as we did for the primary particle and the detector construction. We will pass it in the constructor. So instead of leaving it empty, we pass your event action asterisk event action. We save. What will happen if we try to compile this? We change the declaration, but we didn't change the implementation, the CC file. Do you think it will compile or it will be okay? And it will be okay, or it will fail miserably? Yes, correct. So the declaration, sorry, John, I think there is someone trying to enter the room. So effectively, so someone in the room answer. So the declaration, which is this, and the implementation should match, because the implementation still has not been changed. It will give a compilation error. So we have to edit that file. So we open it with gedit source your step in action. And we have to change the signature of the constructor, because now it's taking as argument a pointer to the event action. I will change this. We can put commas. So the internal private member that we just declared, f event action, will be initialized to event action. Very good. And now we have to update it actually. So we type f event action pointer add energy dep. Underscore MEB, if you wanna keep it. Actually, we will simplify this and we will remove already all of this. the printout. Oh, well, we can keep it. Sorry, we can keep it. For the moment, it's okay. We will remove it later. Okay. Okay. So do you think now the code will work, or we're still missing something? We just changed since the last compilation the signature of the stepping or your stepping action constructor. No. Oh, yes. Sorry. Yes. Yes, because we are using it. Thank you. So yes, we were missing the include. Good. Thank you. Your event action.hh, because we are using it we are using this method of the event action. And do you think it is enough, or we need to change something else? Okay. Does anyone have something against? So in the stepping action.hh, we included the forward declaration to the event action, and we included the header in the CC file. Are you missing something, or do you think it is okay to simply change a constructor like this and expect that nothing else will change? No, we don't need to override the constructor. Okay, let's try to compile and see what happens. So we can compile using this other way. For example, from the intermediate application directory, cmake space -- build. So this is a new error. Error no matching function for call to your stepping action, your stepping action, open close parentheses. Candidate your stepping action. The compiler is kind. I believe that long time ago, the compiler was not so kind. The compiler is already telling you that maybe the function or the method that you want to use is different. So we have to pass by argument to the constructor of the stepping action the object of stepping, of the event action. So to do so, we have to edit the file source, your action initialization.cc, which is where the stepping action was being created. This is the line that was creating problems. We didn't have a constructor without arguments. Now our constructor, the only constructor of the class, is taking an event action pointer as argument. We have to pass it like this. This is the line that we just modified. Any error? Inspected. So now we can compile again, for example, with cmake space -- build. Now it seems that everything compiles. We can try to execute by typing /build or application space Geant4 run.mac. And if we take a look to this, I will not do the math, but I hope someone here can do it almost by head. If you sum up the energy deposited per step, will correspond to the sum up at the end. However, we were interested just in the energy deposited in the target volume. And at the moment, we are summing up all the energy deposited by all the particles. By the way, do you think it makes sense that if we inject 10 MeV electrons, the energy deposited, total energy deposited everywhere is 7 MeV? Does it make sense to you? Or how would you interpret this? It went out of the box with 10 MeV minus 7 point something energy. Very good. So now we still have to change the stepping action because we only want to accumulate the energy if the energy was deposited in the target volume. So we have to go back here. Sorry, before editing any file, how the stepping action will know about the physical volume of the target. The step in action, as the primary generator, do not know anything about geometry, right? A priori, these are completely disconnected things. So we will have to use the same trick as with the primary generator. We will have to pass a pointer to the detector constructor, because the detector constructor is the class that will know about the geometry. So in order to add yet another argument to the constructor, we have to include your step in action. We have to edit it. We have to pass construction. Okay. And we will do exactly the same trick. We have to add a second argument to the constructor of type your detector construction pointer. And then we will initialize a private member pointing to this construction asterisk f detector. And we have to add also the forward declaration, your detector construction. So we have to do something similar to what we have done for the event action. We add a forward declaration here. We add a second argument to the constructor. And we add a private member. Okay. Now we have to change the implementation of the step in action. So we open with gedit space source your step in action.cc.
Sorry, I missed what we just added to the private.
Yes. So we have to do a similar trick that we did for the event action, but with the detector construction. We have to do this because we want to accumulate the energy during the event, but only if the energy was deposited in the target volume. And in order to retrieve, to compare if the step was done in that volume, we have to compare with something. So we will interrogate during the step, is the volume where we are the target? And to retrieve that information, we have to interrogate the detector construction, and to do so, we are going to store this pointer. Good. Now we have to edit this. So we have to add your detector construction asterisk de. Okay. Sorry. So we add the second argument to the constructor as we did in the declaration. And we initialize the internal member. Okay. Now, at this point, we can already comment out this printout because we will not use it, at least for the moment. And we can ask if f detector get physical volume of get target physical volume. Let get target physical volume equal current physical. Let's abbreviate it a bit.
We don't have current TV yet.
Yes, correct. So we have to So just to recap, we have added the second argument to the constructor. We initialize the internal pointer to the detector construction. Now we are going to encapsulate the add energy method in an if. So we are going to add the energy only if we are inside the target. To do so, the condition will be if f detector get target physical volume equal current volume, you can read it the other way around if you want. If the current physical volume where we are is the one of the target, accumulate energy. Now, how to retrieve the current physical volume? We only have access to the step. So we can take a look to the documentation of G4 step that we had open a moment ago. You don't have to do this. I will do it for you. So when you don't know the classes, you can go to the documentation. This is the oxygen where we were a moment ago. You see that the step contains a delta information. Before and after the step, we are going to take the pre-step point. Because if you remember, the post-step can be already in somewhere else. So we take pre-step point. Let me cross-check. Okay, the pre-step is just a step point, and we will use get physical volume. Okay, so we will use this method. As you see, the step points contain a lot of information. So this step in action gives you access to the most inner part of the simulation, the step. Basically what is happening at the step. So we will use this other method, get pre-step point, and then from the step point, we will get the physical volume with this. Okay, now we are going to concatenate these two functions. So we go back to the code. So we say step get pre-step. Get pre-step point.
With the symmetry argument, I could now argue that we could also use the post-step point. Would that make sense? Is there any reason why?
Do you want to answer, John?
Sure. The step actually happens in the volume of the pre-step point. The post-step point is calculated if you arrive at a boundary for the purposes of optical processes, for the purposes of maybe allowing other things to prepare for them for something else. So the volume of the current step is the volume of the pre-step point.
You remember from the slides, in case of a boundary crossing, the post-step will be logically already on the next volume. So that can be misleading. So the information should be taken from the pre-step point, and then we use get physical volume. Okay. Does it look good to you? So from the step has a pre-step and post-step. The step represents a delta of information. We are going to access the pre-step point, and then from that, we are going to retrieve the physical volume where this spatial point was, where the particle was in this step point. Does it look good to you? Okay. Do you think it will compile? So we already included G4 step. Let's see if it compiles.
It didn't change the constructor.
Very good.
I just read it.
So someone already noticed that we changed the constructor of the your step in action, because now it has to take two arguments, being the second one a pointer to the F detector. So we have to pass it here.
But these are the type of things that we can allow the compiler to remind us of.
Yes, these people are very smart, so I cannot play that game too much.
It's perfectly fine to allow the compiler to take part of the load for you.
Yes, sometimes it's better, and the compiler message actually will tell you that what is the error with high verbosity. Okay. So again, we can try to compile by using, I will clean that. So we will compile by using cmake space -- build space build. So close. We were so close. We changed this line in the file your action initialization, where we are constructing the your step in action, simply adding. Yes. Okay, and now we go to the compiler error. So cannot allocate an object of abstract type G4B physical volume. So we can go back to the documentation. Yeah, sorry, thank you. I was missing a point, an asterisk here. Yes, thank you. So we cannot create objects directly. We can create pointers of abstract classes. I was missing here the pointer, the asterisk. But yet there was, we can try to recompile, there was a second error. Did everybody reach this point? I still get one error. Do you still get it too? Okay. So let's read the error message together. It says error invalid use of incomplete type class your detector construction. We are only saying forward declaration. We have to do the full include because we are using a method of the class. So in the step in action, it's not enough with a forward declaration. We have to include your detector constructor. We were missing this header. We can try to recompile again once more. Sorry. Construction. Sorry, your detector construction .hh. Now if we try to recompile once more, there is yet another error message. The error reads as error class your detector construction has no member named get target physical volume. And still the compiler is smart enough to tell us that there is an internal member of your detector construction that has a very similar name, but also tell us not accessible from this context because the member was private. We need to implement the getter. We forgot to implement the getter. This was an example of bad practice. We implemented an internal member, but we didn't expose it when we intended to. So to fix this, we have to edit the file with gedit space source your. Sorry.
And the idea in the end is that we compare two pointers.
Yes. So we can sorry. We can guess the volume where we are, for example, by name. That is terribly inefficient because comparing strings, the compiler or the functions will go character by character until some character will be different or not. And while comparing a pointer is basically comparing to memory address, that is much faster. So whenever it is possible, please store pointers to materials, volumes, whatever it is of interest for you. So comparison of pointers is possible and much faster. To fix this, we have to modify your. So the question was why we are comparing pointers. The answer is because it is much faster than comparing the name of the volume, for example. Now, to fix this compilation error that we are missing the getter, we have to modify the header class, the header file for your detector construction. So we open it with gedit space include your detector construction.hh. We see here the variable, the internal member. We had getters and setters for the target material, the thickness, and others, but we forgot to put this, a getter for this internal member. So getter for the target physical volume, G4, we have to add a new method to the class to expose, to return this. So we can say G4 be physical volume. Very good. We have to say, whenever it is possible, we have to add constantness in our code because we don't want anybody to change it, because nobody should change it. We can say that the return value is not yet a pointer to the physical volume, but a const pointer. So nobody will be able to change it. So we type const space G4V physical volume asterisk get target physical volume, open close parentheses, return, and name of the member that I already forgot, F target physical volume. Okay. Now, do you think it will compile? Or we are still missing something? Very good. Yes. It's never too bad to add const wherever we need it. So we can add another const just to say that the getter is const. We can actually do it with the other const in the other getters too. For example, here, and we did it with the other getters for the material and the thickness. And also, notice how we put this for the material. Very good. Thank you for noticing the const of the return value. So now we have the getter. We can close. We can try to recompile. And it compiles. Let's try to run. So we type ./build/application space G4run.mac. And well, we were simulating just one single event. But if you remember from the previous run, I think I had it open somewhere here. But anyhow, before it was slightly bigger, or no, it was very similar because the energy lost in the G4 Galactic, in the world volume, it was very low. Anyhow, now we have run this. We can modify the G4 run.mac. We can run more events, for example, 10 events. I can keep it open somehow here. Okay. Okay. Yes, thank you. We can run again, and if we increase the number of events that are being simulated, we see this. So we see different numbers for different events. You remember Geant4 is a software toolkit that implements Monte Carlo algorithm. It means that if we run several events, the output will be different, but still reproducible. Yes.
George, sorry, when we set outside of the target to be galactic, so I expect not to have any interactions there. Do we have any interactions? Or
This is a good question. So let's go back to the G4 run.mac and let's put back tracking verbose too. You don't have to do this. I will do that just to show the answer. I will make the terminal bigger and I will run again.
But by all means do it. I don't see why not. Everyone can try it out if they want to.
Yes, of course, yes. You are free
Experiment.
to try out whatever you want. And of course, you might discover even new things. By playing with this simple application is the best way of learning. So let's see. I am trying to look for next volume. Okay, so actually, it's because there is a bit of decalage between the output and the volume and process name. It's a bit confusing, but you can see that even transportation process has an energy loss associated to it. This happens because there are some processes in Geant4 that happen during the step, and some energy loss may happen even if no other process is active. In this case, the energy loss is very low because the G4 galactic corresponds to hydrogen gas at millibar pressure and resembles the outer space composition. So the energy loss in this material is very low, but not zero, because one property of the G4 materials is that their density must be above zero, which means that something at least will happen. Thank you. John and Gabriele, there is a question asking if we can put pure vacuum. Pure vacuum means with zero density. So why we cannot define materials with zero density?
Well, for one thing, there's practically no difference between galactic and you could even put even lower densities. But if you put exactly zero density, all these formulas that we have carefully utilized in there, shall we say, be challenged by zeros. So you can put a very small value, but floating point numbers, there may be somewhere where you divide by zero, that you divide when you in particular, when you look at the length a particle can go, you're dividing by a quantity which will be the density. And because, of course, if you divide by zero, you get not a number. We do not allow this. I'm not sure if we check it everywhere, but by all means, try it out and see how much fun you will have. You will not have very much fun with the Geant4 if you do.
Thank you very much. Still, there are maybe workarounds because, as it happens in many other places, there are many ways of achieving what you want. For example, you can suspend some physics in a given volume, for example, and this will be shown in the advanced course if you want to learn more about that. Okay. Any other questions? If not, so what if we have more than one primary particle, what Geant4, so the question was, what happens if there are more than one primary particles? What will happen is that Geant4 will track them all together, and the information that at the moment would be separated in 2 events, for example, will happen in one single one. So the energy deposited in the target volume would be the equivalent of 2 events in which there was only one primary particle. So if the question is what is better, to run one event with 2 primary particles or other way around, I would say it's always better to run several events for clarity, or doesn't matter?
It depends completely on your setup and what your requirements and boundary conditions are. At first, by all means, do it for clarity purposes, one event at a time. But if you want to run 100 million events, by all means, bring them into, 100, 1,000 per event. And if you have a lot of primaries, then it probably makes more sense to do that, because there are things that can be done per event. For example, if you were to save your random number seed, then run enough simulation, run enough primary particles so that you're actually running for a second or 2 and then save you, and then allow the seed to be saved, or else you will slow down your program.
Okay, thank you for the question. Are there other questions? Okay, so we can simply return to tracking verbose 0, and we can run it again. So what we have here is the energy deposited in the target volume in 10 different events. You see that the numbers are different. Imagine that you want to calculate the average. So you could simply print out or save these values somewhere else. For example, using G4 analysis, which is a module of Geant4 that maybe we will cover tomorrow, maybe not, but basically allows you to save at the end of the event, typically this quantity in, for example, in a root T3, and save it by you without having to implement any T file or T3 by yourself. G4 analysis will do it for you. Or we can we can do it ourselves. To do so, we will have to implement our own run action, sorry, and we will see it in a moment how it is done. So I will go back to the slides. Okay. Sorry. So as a recap of today, we had G4 track as a snapshot, the status, a collection of properties, a status of the particle during the simulation. A step is the delta of this information, and the status of the particle after the step will correspond to the status of the track. The number of particles that will be tracked correspond to the primaries we inject and the subsequent secondaries that the physics may produce along the tracking. The G4 event, the event in a simulation corresponds to the minimal unit of a simulation and will correspond to the sum of all the tracks plus other things that we will not mention in this beginner's course, but you can think about the event as a collection of primary tracks plus all the secondaries that might be created along the way. And a collection of events is called G4 a run. During the run, the events are processed in an event loop. So the internal machinery of Geant4 will start an event, will inject some primaries, will be tracked, and when all the primaries and secondaries are tracked, the event is closed, is considered finished. When all the events are simulated, then the run is finished. At the beginning of the run, some things happen. So if you remember, the run manager is initialized, and that means that the geometry is constructed, the particles are constructed, and the physical processes attached to those particles are constructed. Yet, when the simulation begins, there is still an optimization process for that, an optimization applied to the geometry to improve the navigation, called so an structure and a help structure is created called voxelization, a set of voxels, and some other properties, some other information for the physics is being created at the beginning of the run. During the run, neither the physics, once the simulation of the events start, of the actual events start, neither the geometry, neither the physics can change. That is a good point, that we made a getter of the physical volume of the target const. So we ensure that our interface is robust and is compliant with this design rule. And yet we saw that in the detector constructor, we can change things between the runs. For example, we were using reinitialized geometry, or geometry has been modified to reconstruct part of the geometry, or we can also use physics has been modified to reconstruct part of the physics. But this is something that must happen between the runs. As we have seen before, there are some hooks that allows us to interact with each unit. In this case, to interact with the Geant4 run, we can implement our own run action. And in addition, and this is a bit special, sorry, the user run action allows us to implement our own action at the beginning of the run or at the end of the run by re-implementing these methods. This method, the begin of run action, will be called for starting the event loop, and the end of run action will be called at the end of event loop. And the run manager provides us access to the Geant4 run, similarly to the other managers that we have been mentioning. We will implement now our own your run action, and we will calculate, for example, the average of the energy deposited across the events in the end of run action. And similarly to what we did with the event action, typically in the begin event or begin run, we will allocate or reset some internal parameters that accumulate information, and at the end of the run, for example, we will take some action. We will use this accumulated information for something else. For example, in case of a run, typically in the start of run, at the beginning of run, we will open a file or prepare a file to be written later, and in the end of the run action, we will write down some information, for example. There is another method. This was a bit different with respect to the other user actions that we have seen, that allows us to create a Geant4 run. It's called Geant4 run, and as we can also derive our own run class that, for example, extends the features that Geant4 run offers. For example, Geant4 run can accumulate the number of events that happen, other some basic information, but if we want to accumulate other things, for example, energy spectrum of the energy being deposited per event, we can extend the class Geant4 run, and we can add a histogram, for example, to this and accumulate it, or things like that. We can also implement other methods to encapsulate some actions. For example, we can add our method run summary just to print out this summary information. So now we will add our action, and I am not sure we will have time today to see multi-threading in Geant4, but it's very easy to jump from one to another. So I hope we have time today to implement our own run action, and we can review maybe how the multi-threading works and leave it there before we leave. Any question? Okay, so we can go back to the code.
In the meantime, I've put a poll on Mattermost how people are following with the code. So both here and remotely, please give us a feeling of how you're going along.
Thank you.
Now I need a few minutes to join the.
Okay. So we are going to create yet another class. So we have to start by the header. So we are going to type gedit space include your run action.hh. Okay, ampersand to keep this open. We will start. Well, I will put the file we are, because otherwise maybe you don't see it. Your run action.hh. We will start as always with the preprocessor guards. So if and def your run action underscore hh, define your run action underscore hh hash and if. Now we are going to define the class your run action, and it will derive from Geant4 User Run Action, and it will derive publicly open close curly braces semicolon. As we have been doing so far, we have to include the header of the base class Geant4 User Run Action.hh. Now we will implement the public method, so the constructor your run action open close parentheses semicolon, the destructor your run action open close parentheses override, and we will implement the methods begin and end of run action. So the signature of the method is void begin of run action between parentheses as argument const Geant4 run asterisk is a pointer to a Geant4 run object, and we have to mark it as override because we are overriding the method from the base class Geant4 user run action. We have to do the same with end of run action. The argument is the same, const Geant4 run asterisk override. And in order to calculate the average energy in a run, we will accumulate the energy of all the events, and then we will divide by the number of events. It's a very rough way of calculating the average, but it will work. So we will implement a method void add event edep, for example, Geant4 double event edep. We will create a private member that will be the container where we will sum up all of it. For example, f edep in target. And we can do a so-called inline definition of the function. So this is something that we have been doing only for some getters. We can do it for some simple functions. For example, we can say that f edep in target plus equal event edep. Sorry. Okay, so we have implemented the header. Is everyone in the same page? Okay. It looks very similar to the event action, but this will be on top of the event loop. So now we can type gedit source your run action.cc ampersand, and we can do as we have been doing before. File your run action.cc. We start by including the header of your run action.hh. And we can try to compile at this point and see what happens. Do you think it will compile or not? So there are many things that we didn't define, but if you remember, we tried to do this before, and we are overriding some functions, so we are doing a strong promise to the compiler, but we are not implementing them, so it will crash. It will not allow us to compile. So we can. The first thing we have to do is to update the CMake cache files, because we have introduced two new files, the yourrunaction.hh and yourrunaction.cc. So in order to update it from the main directory, the main directory intermediate application, we can say cmake space -s dot -v build. This will update the internal cache of cmake, and now it knows that there is a new file, and now we can recompile by typing cmake space --build. Now it builds. Okay. Let's continue.
But why does it compile if we said we will override some function, but we never do? I thought it should fail.
Let's try to define the constructor and let's compile again. So we can define the constructor. That is very simple. So your run action your run action, we initialize the base class Geant4 User Run Action open close parenthesis comma, and I already forgot the name of the variable. So before we define an internal member called f edep in target. So we have to initialize the value here. Doesn't matter because we will override it later. Shall we try to recompile now? It's very misleading, right? Sometimes the compiler can be cruel. Let's continue with the implementation. If you see an error like this, undefined reference to vtable for your run action, let's continue. The error is not trivial to understand. Let's implement the structure. So your run action tilde your run action, open close parentheses, open close curly braces. Okay, let's try to compile again. Now the error should be different. A bit more understandable. Once we implemented the constructor and the destructor, now the compiler should only complain about undefined reference to your run action, begin of run action. Is complaining that we promised that we would implement these functions, but we didn't. So let's implement them. So back to the code. We have to say void your run action begin of event, begin of run const Geant4 run pointer is not harmful to initialize to reset the variable here in case we do two runs, because if we run once, we call beam on once, it's okay. We are initializing the variable f edep in target to 0 at the very beginning. That is good. But if we call run beam off, or we run two runs, the variable is not reset. So it's always good practice to reset the variables in the begin of run, begin of event, or equivalent. And then we can implement, we can compile, and we will see that at least one of the compiler errors, I will leave it here, at least one of the compiler errors should disappear. Sorry, I made a spelling mistake. Begin of run action, sorry. Okay, so now one of the two undefined references is gone because we implemented one of them. So now we can continue. Void your run action, end of run action, const Geant4 run asterisk, open close, curly braces. We are going to retrieve the number of events. So we can declare a variable called Geant4 int space n event equal to run. Run is an argument to this function. If you don't say anything, it will be ignored. It doesn't matter. If you are going to use it, please add it. It's usually, maybe it's good to leave it. If you put it, you will get a warning from the compiler. It's always good to learn new things. And then from Geant4 run, we have to obtain the number of events. We could check the documentation, but we can also try to see what message from the compiler we get if we ask for get number of events. Let's assume that it has this. We can check the documentation too. We can calculate the average of the energy we can simplify a bit. EDEP average or EBET average, I don't know, like the internal variable where we are accumulating it divided by n events. And then we can print it. G4 cout average energy deposited in the target in MEV, because we were passing already the energy in MEV. Okay.
this is something interesting because FTDEP in target should be a floating point number, but an event is an integer. Is there anything specific about that? Don't we expect this to then give me a
Double divided by integer, the integer gets promoted to a double and the division happens.
If you remember, there is still one trick. And probably you noticed in some places, instead of 0 or 1, I was putting 0 dot. Yes. So this is because if in the first day when we were reviewing the formula to calculate the volume of the sphere, you can see how the code looks like. When I was the formula to calculate the volume of the sphere is 4/3 multiplied by pi, the radius to the third. If you put 4 literal divided by 3 literal, C++ will interpret that as a division between integers. This is not promoted to double, and 4/3, when those are integers, will be 1. So in order to one of the two to be promoted to be a double and the other one be promoted, you should put 4 dot or 3 dot or both 3 dot divided by 4 dot divided by 3 dot if you are using literal numbers. Good. So is everything okay so far? I can make it a bit bigger. So the last piece of code is visible. We can try to recompile again. Almost. So the first error is related to invalid use of incomplete type. What does it mean, incomplete type? We didn't include Geant4 run. If we include Geant4 run, we have to include Geant4 run header because we are accessing a method of an object Geant4 run. So if we want to obtain the number of events from run, we have to include the header. Now we can recompile again. This is not the member that we wanted to use, the number of events. So it turned out that it's a bad practice to try to guess a method. So what is the conclusion? If you do not know, don't try to guess. Go to the documentation. So back to the documentation. We had today we were checking Doxygen. We typed Geant4 run, which is the object that we were trying to access. And here you see, this is the method. Okay. Why the get number of events is the method? The method is named in singular. You can ask maybe John or Gabriel. Anyhow, now this should compile. Very good. So now we can.
It is a historical mistake.
Here you are.
It is things like that. It would be good to fix.
Yes. The problem is that the interface should not be changed, I guess. Or
one can always have the correct name method and eventually take away the wrong one.
Exactly. But the conclusion, the bottom line of what I was trying to do is please never guess a method. Please read always first the documentation. Otherwise, you might get surprises. Good. So now we have compiled successfully. Does it compile for everyone? Good. So now we can, I will maximize this. We can run our application with Geant4 run.mac.
And we didn't register the end of run.
Ay, ay, ay. So we were missing something. As someone said in the room, now the code compiles, runs, but it does not do what we want. This type of errors are the worst when the compiler, when the program runs and it does not do what you want. It's a bit tricky to understand, takes time. Okay, we have to register the run action still in your action initialization as any other user action. So here we can, for example, do like your run action asterisk run action equals new your run action open close parentheses and register it with set user action run action. Is this enough? Just creating the object in the build method. I will make it. We are missing the include. Okay, now should be fine, right? Very good. I will try to keep it the last part. So we register in the build method of the action initialization yet another action. We have to compile again. For example, with cmake space minus minus build space tilde. We can run build or application Geant4 run. But now the average energy deposited in the target is 0. Why? Because we are not updating the counter of the run action. So the run action now is registered as an action, but it's not doing anything. We are not calling the add energy, or I don't remember, of the run action. So what do we have to do? We have to connect the run action with the event action in a similar manner as we did before. And actually to do so, we have to put the initialization, the creation of the object before. Sorry. So in the your action initialization, we will pass to the event action the pointer to the run action. And we will do something very similar to what we did to the step in action. Okay. So, sorry. These are the lines that we have to change in the build method. We are not only creating the run action here, but we are also linking the event action to the run action in a similar manner to what we did before with the step in action and the event action, or the primary generator and the detector. Okay. So now we have linked it now. If we try to compile, we will have an error that is very obvious, saying that error no matching function to call your event action. So the constructor, which takes an argument, your run action, which is what we try to compile. And the compiler is trying to suggest, maybe you want to use the constructor without arguments. No, what we have to do is to extend the constructor that we have, so we can connect the event action to the run action. To do so, we are going to open the include your event action.hh. I will maximize. Now we are going to do the same trick as before. So we pass as a pointer to your run action asterisk run action. We will create a private member that will be the same type, your run action asterisk f run action semicolon. Very good. And we need to do a forward declaration of this class. Good. So the changes we did to the file, I can put here the name of the file. Your event action.hh. So the changes were a forward declaration. We changed the constructor to take a pointer to a run action, an internal pointer to your run action. Now we have to change the constructor implementation. So to do so, we go to the source, your event action.cc, and the change is rather minimal. We change the constructor in the same manner. So instead of leaving the argument list empty, we have to say your run action asterisk run action, and we have to initialize, for example, in the list, the f run action. Oh no, it was working so well today. Sorry. Oh no. Sorry, my Zoom session crashed. It will take me a minute to. Okay. Please. Thank you. So we have to initialize the internal pointer to the run action as this. So in your event action.cc, we have modified the constructor to take as argument a pointer to the run action. We have initialized the internal pointer to the run action in the list of the constructor, in the initialization list of the constructor. And now, in the end of event action, we are not only to print out, but also we are going to use the method that we declare for the run action to add the energy, which I already forgot. Sorry. So we have in your run action.hh this method, add event energy deposited. So this is the method that we have to call here. So in your event action end of event action, we call f-run action at event depth. For example, we do like this. So in the your event action.cc, we change the constructor in these lines, and we add this line in the end of event action. So at the end of the event, we will update the run action with the event deposited, with the energy deposited by all the particles, the primary particle and all the possible secondary particles, doesn't matter. And with all the energy deposited by all particles, primary and secondaries, in the target volume.
Now we're mixing the constructor list with explicit arguments in the function signature. This is okay?
Do you mean by explicit argument? You mean when we say energy per event 00?
Yeah, exactly. We're not defining energy per event as an argument.
No, the energy.
Is always just 0.
The energy per event. So we are in the modifying the class your event action. So this internal variable energy per event represents the energy deposited by primary particle and maybe other secondaries during the event. So we will accumulate here energy per event. Once the event finish, we will call the run action add event dep here, and we will update the run action. The fact that we are initializing here the variable, it's okay. It can be even omitted because we are resetting the variable in begin of event action. In general, it's good practice to initialize all variables that you use. Good. So we can save, we can close, we can recompile. Aish, nobody noticed we were missing something. So we see an error here, invalid use of incomplete type. This is a error that happens every day at least once. And also the compiler is telling us, watch out, there is a forward declaration to the class, but we didn't include the header. So we have to go back to the source your event action. So gedit space source / your event action.cc. Yes, sorry. Thank you. I will try to keep the error visible for everyone and how to fix it. So this is the error, and this is how we will solve it, by adding an include, by including the header. Okay. The compiler error reads as invalid use of incomplete type. Note forward declaration of class, your run action. It means that we were missing this include in the file your event action.cc. After adding this header, we can try to recompile. Well, we can close this already. We can try to recompile, and it compiles. We can try to run, to execute. So / build or application Geant4 run.mac. And now at the very end, we see this line, average energy deposited in the target for dot blah 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 MEV. Very good. Is everyone here? Okay. Let's. Okay. So in the event, in your event action header, we change the constructor. So now we are doing the same trick as we did for other classes before. We are passing as argument to the constructor your run action. So we are connecting your event action to the run action, because we want at the end of the event to update the energy deposited in the target. To do so, the first step is to connect them by storing a pointer. To do so, we change the constructor. We add a private member that will hold this pointer, and then in the your event action.cc, in the method end of event, we call this f run action object. We call add energy. So we update it with the energy deposited during the event in the target volume. Okay. Does it answer the question? Okay. Now, this is good, but so far we have been running in one thread. So let's do it slightly different as before. Let's move to multi-threaded. You will see it's very simple. So we open gedit space or application.cc, and we are going to comment line 33 that was limiting the number of threads to 1. And now Geant4 will choose whatever it wants. By default, if Geant4 is compiled with multi-thread, it will, as it is now in this version, it will choose a multi-threaded run manager, which means that we will see something interesting now. So we just commented this line that was limiting the number of threads to 1. We can close. We can compile again. And if everything works as expected, now we should see something else. Very good. There was something else changed before, but the message is quite long. Do you notice any difference? What are the differences? Do you notice?
We have 2 times average energy deposited output.
Okay, so now we see 2 messages saying so this printout was at the end of run action and end of run action. So it means that now there are 2 run actions being created.
It's no longer completely deterministic because the output is not 9.
Ah.
At least the order seems to be random.
Okay, and also you notice that the prompt, the prefix that is in every line now is different. Now we see G4, WT0 or 1. These are the different workers that Geant4 start in multi-threading. Okay, so now we are in a point where we can explain a bit the multi-threading, I guess. And with this, we will finish the session of today. We will go back to the slides. Okay, if I can.
It's quite important to have at the end of it some summary function.
We need something a bit more sophisticated than a summary function. Okay, so far we have been doing a trick. We have been using a trick, which actually is a bit oldish now. That is using your run action to accumulate to the energy deposited per event. But actually, what we should do, and we will do it tomorrow, is that we should create our own run object. And is this object the one that will store the energy deposited per event? The reason for this will be to make it compliant with multi-threading, and we will see now in a moment. But first, a note about multi-threading. So, as we said the first day, the simulation, every event in Geant4 is independent one of each other. So if we start an event with a random seed, we will get always the same, but the events are simulated independently. Let's say the history, the geometry, and the physics are used as if nothing happened. It means that we can, for example, apply some parallelism. We can simulate the events independently in different threads. And as a note, between multi-threading and multiprocessing means that we will execute many times the same application. But it means that the memory that will be used is different. Each program is isolated from the rest. If you can launch several times the same program, and each one will have their own memory space and no data is shared. Multi-threading means that you execute one single program and the different threads can see some shared objects. The threads can share some components. For example, in case of Geant4, we can share parts that do not change during the simulation. This sketch will try to represent the different options. So in a sequential application, you have one application. In our case, is what we had at the moment until we disable the limitation in the number of threads. So the memory will be assigned to that application. Nothing is shared, nothing is seen from outside. We can launch the same application many times, and it means that if our application needs 1 GB of RAM memory and we launch the application 4 times, we will be consuming 4 GB of RAM memory plus other resources. So each time we execute it, it will require n times. If we execute the same application n times, we will need n times the resources. In multi-threading, we try to optimize a bit the use of resources, in particular the memory. So we will have we can have several threads. A master thread that will own the memory space and can create some shared objects, for example, the geometry or some parts of the physics, and other threads can carry out the simulation itself, for example, by simulating each one an event. This is a schema of how the multi-threading is implemented in Geant4. So we can say that the first thread is actually the thread 0 is creating the geometry and the physics configuration, while the other threads can have their own event loop independent from each other. If there are some components that may be modified by the worker threads, this has to be marked, or it's created as thread local. It means that each thread will have a copy of that part. Some parts of the physics, the fields, and if you want to collect some information per event, this will be thread local information. For example, a collection of hits will have to be thread local. You don't want to mix a collection of hits from 2 different events. This is a graphical representation of on the top how the resources are shared in a multiprocessing schema, and memory might be a limiting factor that can prevent us from using all the CPU power in a machine, while in multi-threading we can reduce the amount of memory that we use because the same geometry and physics can be shared between several threads. These are components that will not change during the event loop, during the simulation. So how the multi-threading is achieved in Geant4 is that these objects that do not change, the detector and the physics, are created directly in the main program and registered directly into the run manager. And the user actions, we have been registering the user actions in this build method. But if we run in multi-threaded, we have also to define a method called build for master. This method can create their own user action, which can be different from the workers. For example, we can have a dedicated user action to open and close a file, while the worker run action, for example, can do something else, because maybe we don't want every worker to open and close a file, because maybe it's the same, whatever reason. So the only user action that we are supposed to create in this build for master is the run action, while in build we will keep it as it is. So in build will be invoked by every worker, and we have to put here as minimum the primary generator and plus all the other optional user actions, the stepping, the event, and the run action. The reason for this is because everyone has to be able to generate a G4 run object, even if in master the G4 run is not used. During the simulation, the master G4 run object is not used, but at the end, the master will invoke a method of the G4 run, which is called merge. And basically, you can imagine this G4 run object as empty during the simulation loop, during the event loop. And as the threads are finishing, so when each thread called the end of run, or after the event run for that thread, it will merge the G4 run of that thread to the master. So the G4 run object of the master is like a container for the other G4 runs. And in order to sum those, we use the method merge. And at the end, the master G4 run object will contain all the information collected during the runs for the independent threads. So as you were saying before, we need something kind of summary, but it's not actually summary. It's more like this merge method. We need to sum the different G4 run objects from each thread, from each worker thread, into the master. And the implementation of this, we will do it tomorrow. I do not know if maybe we can leave it here, or you want to do a recap?
I have a question which was from just before you started discussing multi-threading. I've answered online, but I think it's worth that someone keeps getting a higher amount of deposited energy, around 9 MeV, although the injected energy is the same. What could be the reason? I'd missed that the kept getting, so the average seemed to be higher, but certainly my response was, of course, that there's no obvious violation so long as it's less than the original particle's energy. And if it was just occasionally, it could be that the hardware is different. This one is running on an Intel processor, the other one's running on an ARM processor. You get different floating point numbers, and the simulation runs differently. But in more general, it smells as though the different material is being used if more energy is being deposited in the actual volume. And I suggested investigating using tracking verbose 1 or tracking verbose 2. I don't know if you have other suggestions.
To review your detector construction.cc, where we are setting up in the constructor the material by using set target material.
Maybe the size of the detector was also different.
Yes. So so far, what we were trying out is 1 centimeter of G4 silicon. So material is G4 silicon, and the thickness is 1 centimeter. So in summary, for multi-threading, the idea is that the workers are independent because the events are assumed to be independent, and we only need to implement this merge method for the G4 run that we also have to derive, just to sum up everything. This is the manual way of doing this. The alternative is to use G4 analysis that will do all of this for us. If we use G4 analysis to record our data out, we don't need our own run action. We do not know to implement our own G4 run or this method merge. G4 analysis will do all of that for us. We only need the event action, and at the end of the event, we will tell G4 analysis, please add a new event in our output tree, or add a new entry in the histogram, and G4 analysis will take care of summing up everything at the end of the run. Yes.
So when we want to do the multi-threading, for example, I have 10 threads in my PC, okay?
Yes.
Then should I keep one thread just for this merge, or I can use all of my threads?
So thank you for the question. So is the master thread the one that will be calling the merge? So the master thread will own a Geant4 run object, but because it's not running any event, it will remain empty. And only when the worker threads finish their own number of events, they will have been produced their own run object with some information. Those will not be empty. And then the master that owns this empty run object will start collecting those and summing up to its own. So during the master is not doing any simulation. It's used only at the end to sum up everything.
Practically speaking, it depends what you're trying to do. If you're trying to use your own laptop at the same time as trying to run a Geant4 simulation, maybe you don't want to use all the hardware threads or all the capability of the machine. You want to keep a little bit behind so you can use the machine interactively. If it's your server and you want to let it run over the weekend, by all means, run all the threads that you can and maybe add a couple more in case the machine is, it tells you that it has 10 cores, 20 hardware threads. Add a couple more, you might get a little bit of extra performance. Of course, so long as you have a reasonable amount of memory. But other than that, go for it. Try it out.
Thank you, John. That reminds me, please, if you use any batch system, such as the one at CERN, please don't over-abuse it, because the batch system of CERN does not check if your application is multi-threaded or not. So you can always, in principle, cheat, request one single CPU, a single thread, but your application might be multi-threaded. These end up with a potential collapsing of the node, and restarting the node will annoy many people. Please don't do it.
So how do we prevent this?
Sorry?
How do we prevent this?
So when you launch a job in the Condor batch system, you have to request a number of threads, but that number does not, nobody will check if the number of threads that you request is the number of threads of, for example, your Geant4 application. So you can request one thread to the batch system, but launch your application with 100. What is going to happen in practice is that you will be stealing CPU time from other people, but also eventually can lead to the collapse of the node, where all the works, not only yours, are running, and that will affect yourself and other people. And eventually an investigation of IT will point to you. So please don't do it. It will save time for everyone.
So we're supposed to request the number of threads that we will actually use.
Yes, that is the point. If you submit
on your own resources, you can try whatever number of threads you like.
Yes.
You will see how effective it is what you're using. On shared resources, you have to be responsible, as Alvaro says. And certainly, even when you're using your own resources, you can leave it free, and Geant4 will try and guess how many threads you can use on your machine. You can see whether that works well or not. You can set it, because you might want to run 2 different simulations at the same time. So you have 8 cores. You might want to use 4 for one, 4 for the other, because you want to run different configurations, or because you believe that was good enough and you'll get the results soon enough. It's certainly up to you.
And in case you are doing some kind of benchmarking of Geant4, Geant4 also offers some internal tools to fix the affinity. It means that in normal computers, your thread will be jumping from maybe even from one CPU to another. That is annoying, because this can slow down or it may have an impact on your benchmark. Geant4 offers internal tools to fix threads to a fixed CPU, and then it's a feature that you can use.
This is also not encouraged on shared systems.
Yes.
If you're sharing a node, then you accept whatever is given to you. You don't pin.
Yes. This is only for benchmarking for very specific applications. Okay. Maybe something else that I have been forgetting every day, and I think it's a mistake from my side, is to advertise here. a contact point. So I have been speaking about different sources of information. So we have the user guides, we have the document, the source code, very well. But what if you need assistance beyond ChatGPT? So if you want some human interaction, Geant4 offers the Geant4 forum, and if you have some question that is properly made, you will get answer. Depending on the details and the complexity, it will take a bit less or a bit longer. And this is a good entry point in case of in case you need further assistance. For the more advanced users, in case of in order to access the Geant4 forum, you can access it from Google. You can access also from the main web page. For the more advanced users, if you ever find in the remote scenario where you find a bug, because this is not something that is happening every day, you can report here in the Bugzilla system with the maximum level of detail possible the problem. There are some rules when reporting errors, because if you simply say this does not work as I want, your ticket or your comment will never be answered. But if you provide a reproducer with an explanation of the expected behavior and the actual behavior of Geant4, developers will pay attention. The amount of attention that developers will pay to your complaint is more or less proportional to the level of detail that you give. If you will not give too much detail, developers will tend to ignore your ticket. If you provide a code reproducer and an explanation of what is going wrong, developers will be more eager to attend your complaint.
There is one other resource, which is an obvious resource these days that Alvaro has not mentioned, that your LLM of choice has likely read the Geant4 documentation, or you can point it to it, and you can ask from something from basic questions to reasonably medium level questions, and you will get reasonable answers. No perfection, but you can get quite a lot of help that way. So you will not generally, we do not generally expect these days to find basic questions on the Geant4 forum. But of course, if you think that the answer that you might get from other sources does not make sense, by all means pose them as well.
And again, ChatGPT as the Thermomix has a range of applicability. So for example, ChatGPT has a threshold after which ChatGPT in free mode was not trained, has not been updated. And there are some features that have been added in the meantime to Geant4, and ChatGPT do not know about them. So you have to be careful, because if, for example, you ask ChatGPT, can I generate a screenshot offline in batch mode without the need of installing third-party libraries like Qt or whatever? ChatGPT will tell you, no, that is impossible. How you dare to ask that? Because this was a feature that was introduced 4 years ago or 3 years ago. And I believe the threshold for ChatGPT is 2022.
As I said before, you don't need to rely on it for everything, but your LLM of choice likely will have a reasonable basic answers, and especially if you point it. If you say, look at the documentation of this version and this guide and this and that and the other, there's a high likelihood that it will be more specific. But the idea of taking this course is that you'll be able to understand things more and look at the documentation yourself more. But if you don't understand the documentation after you've read it a couple of times, number one, send us a message. The documentation is not understandable, and explain what you were trying to find. And number two, by all means, use other sources.
So the idea of this course is not that you will understand everything. Geant4 implements like 7,000 or 8,000 classes. It's impossible to learn that in 1 week. But the idea is that you will get, hopefully after tomorrow, a solid basis of how to grow your knowledge out of that. If you simply ask ChatGPT, it will give you maybe the answer, which might be right, but the knowledge that you will grow is a bit limited. So it's always a bit better if you have the time to try out, to play, and to learn by other means. And otherwise, I think we can conclude here. So thank you very much, everybody, and I hope to see you tomorrow.